Hello everyone. Today we will see the concept of non-deterministic finite automata. Non-deterministic finite automata is going to accept all those strings the deterministic finite automata is accepting. The only difference between deterministic and non-deterministic is that non-deterministic has the rules are relaxed, while when we are designing the machine the rules are relaxed, so it will help us designing the complex machines. And eventually we will see the algorithm that where we can convert the non-deterministic finite automata into finite state machines. So for now, see the definition. Non-deterministic finite automata is defined by 5 tuple Q sigma, Q naught, Q sigma, Q naught, A and delta, where Q is finite set of states, same as the deterministic finite automata. Sigma finite set of symbols, again the same. Q naught belongs to Q, that is the initial state, it is also same. Set of accepting state or final state, A is the subset of Q. That is again the same concept that is we have seen in the deterministic. These 4 tuple remain same as deterministic finite automata. The transition function here is defined as Q cross sigma to power set of Q. Q cross sigma to power set of Q. Take any example where suppose we have states Q0 and Q1, sigma A and B. So Q cross sigma will have elements Q0 A, Q0 B, Q1 A, Q1 B. And power set of Q will have phi, Q0, all the subsets of Q0, Q1, Q1, Q0, Q1. Take this example, Q0 on reading A, it goes on Q0, Q1. It is associated with this element Q0, Q1. It means that Q0 on reading A can have two transitions, Q0 to Q0 as well as Q0 on reading A, it is going on Q1. See this, it is going on Q1 as well as it stays as at Q0. So we can clearly see it was not there in the deterministic finite automata. For deterministic ones, we have seen that every element will have exactly one transition on any state. Whereas in this case, in non-deterministic, it allows more than one transition. On reading Q0, the state Q0 on reading A can go to state Q0 as well as can move to the next state, that is Q1. Also, we can clearly see that we can skip some of the transitions in the non-deterministic finite automata, as we can see that this Q0 doesn't have any transition on B. As Q0 on reading B is associated with the element phi. It means that it doesn't have any transitions. So it makes the rules relaxed, and while designing the machine, we'll see the simplicity. When the language is very complex, non-deterministic finite automata will be designed easily comparatively for deterministic ones. And finally, we can convert non-deterministic finite automata to the deterministic ones, because remember that deterministic and non-deterministic finite automata are accepting the same language, that is the regular language. If some language is accepted by non-deterministic finite automata, it is also accepted by deterministic finite automata. That is, we have equivalence that we'll see in the later videos. Suppose I have this example of non-deterministic finite automata. We need to create a machine, design a machine for non-deterministic finite automata for the given language. The language sigma is A and B, and the language is A raised to the power n, that is any number of A's. That is, the regular expression for this is A star. We can simply design it Q0, any number of A's. For B, we have not given any transition, as It is not required. By the definition, Q0 on reading A is going to state Q0, and Q0 on reading B is associated with phi. So the diagram is so simple. We do not need to have a trap state or anything like that when we are creating the non-deterministic finite automata. See the next example. A raised to the power n, B raised to the power n, where n is greater than or equal to 0. So we will have this Q0, any number of A's, Q1, any number of B's. For the transition from Q0 to Q1, machine can transit from Q0 to Q1 either reading an A or a B. So simply A comma B here, and this is the non-determinism. Any possible combination of A's, that is any number of A's followed by either A or B, and then followed by any number of B's. Then we'll see some more example. String starting with a double A. A non-deterministic finite automata for the language where the string is always starting, all the strings are starting with a double A. Simple one. See, the regular expression for this is double A plus B, whole clean closure. We are just mapping this expression in this machine. We are seeing that Q0 on reading A is going to Q1. Q1 on reading A is going to another state, say Q2. And on Q2, it is an accepting state. The requirement is fulfilled. It can be followed by any possible combination of A and B. We are not required, we are not forced to show the transition of B on Q0 as well as of B, the symbol B on Q1. Where if you are making deterministic finite automata, we need to have the transition of every symbol on each of the state. So making a non-deterministic finite automata becomes much simpler comparison to deterministic ones. String double A as a substring. Every string must have at least one double A as a substring. So just take this A, reach the accepting state. And then we have any possible combination of A and B. Here too we need to have any possible combination of A and B. That is, the regular expression here is A plus B whole clean closure double A plus B whole clean closure. So we have just mapped this regular expression in this machine. See, Q0 on reading A is going on Q0. Q0 on reading B is also going on Q0. Q0 on reading A has double transition like this. Q0 when reads A, it can go to a state Q0, Q1. It means it is going to the state Q0 as well as Q1. Q0 on reading B is going to state Q0, and Q1 on reading A is going to state, if this is Q2, similarly Q1 on reading B is going to phi, and Q2 on reading A, Q2 on reading B, both of these are going to state Q2. So this is the function mapping delta. Delta of this particular diagram is working like this. The next example we have here is a language L that has AA or AAB whole raised to the power n, means any combination of double A or double A followed by B whole clean closure, and then the final symbol is B. For such type of language, if I try to make a deterministic finite automata, it will become really complex while designing. So the good idea is that first of all make the non-deterministic finite automata for such complex language, and then we can convert that into deterministic finite automata. So let me start with Q naught. It says AA or AAB, AA or AAB. AA, make this as the final state. Now we can see that what's the combination AA, see this path A, A. This is the loop A any number of time, or A, A, B any number of time in the loop, and eventually finally the either AA or AAB will always stop on Q naught. Q naught should read 1B. This path should be followed to reach the accepting state, that is Q4. So whenever we have such type of language, go for a non-deterministic finite automata. Design it well, because of simplicity, we can easily design this structure here, and finally we can convert this into deterministic finite automata using the algorithm we'll be discussing in the next video. Take one more such example. Suppose if I give you a language L, where we have the requirement that this is A plus B raised to the power n, AA or BB, A plus B raised to the power m, where n and m greater than or equal to 0. So for this, what we will do, start with Q naught. Q naught on reading A, there are two directions. Q naught on reading A will stay on A, as well as it will move to the next state Q1, and Q1 on reading A will move to the next state, say Q2. Make this Q2 as the final state. Q naught on reading B, Q naught on reading B should stay on Q naught, as well as Q naught on reading B should move to the next state, say Q3. Q3 on reading B should go to Q2. Q2 on reading A or B should stay there only. Q2 is the accepting state. We can see that AB, any possible combination of A or B, that is AB whole clean closure followed by a double A or double B from this path, and then again A plus B whole clean closure. So this is one example. Now I'll give you one more such example and you all can try. Suppose if we have a language AB, A plus B whole raised to the power n, double A or double B. This also raised to the power some t, and then A plus B whole raised to the power m, such that n, m and t all greater than equal to 0. What should be the diagram non-deterministic finite automata for this? First of all, see, we can have a possibility of null, because if n is equal to 0, this will become null. If t is equal to 0, this will become null, and m is also 0, then it will become null. So we have a null string. Make initial state as a final state. And then AB whole clean closure. Put this AB whole clean closure. The loop will make AB whole clean closure. And then again, take this A Q1 and this loop AA any number of times, or BB any number of times. That's it. This is the diagram for the given language. We can see that AB whole clean closure followed by AA or BB any number of times, stopping on Q0, and then again AB whole clean closure. So this is the diagram for the non-deterministic finite automata for the given language. I hope you all are getting the concepts of automata. I'll have one more concept on non-deterministic finite automata with null transitions. We'll see in the next video. Thank you for watching, and please follow the concepts regularly. Do let me know your doubts, and wherever you have some new question on the automata, give the question in the comment box so that I can solve and send it to you all. Thank you so much for watching.